Hello, everybody. I believe I'm recording right now. Okay, I am. All right, so we're going to continue where we left off in slide 12 of Orgo Lecture 5. So we left off with the formation of the Grignard reagent, in which we have a nucleophilic carbon group due to the metal donating its own electrons since it's electropositive. So what we want with the Grignard reagent is to tackle this electrophilic carbon right here. However, in order to do that, what we're going to need to do is make sure that there is no acidic hydrogen laying around that can possibly be taken up by this nucleophilic carbonyl group. Because remember, sorry, not a carbonyl group, the alkyl group. Because remember, if we have an alcohol group and we have this very strong carb anion, aka our nucleophile, if that nucleophile had the choice to either choose between the electrophilic carbon or this alcohol's hydrogen, is going to choose the alcohol's hydrogen. Another example would be like if we had a carboxylic acid. We're going to need to protect these OHs to make sure that our carbon group attacks the electrophilic carbon that we want it to attack. Okay, so how can we protect an alcohol group? So what we can do is add groups such as mesylate and tosylate, which will act to replace the hydrogen on the oxygen of the groups that we want to protect. And then once we were finished our Grignard reaction, for example, then we're going to remove those protecting groups with just a reductive solution. So what would this look like? Well, let's say, for example, we have this group right here, and we wanted to protect this alcohol group. So then we would add our, for example, mesylate. It's a Cl here, and a methyl group right here. So what would happen is that the OH would be deprotonated by the solvent. The solvent is going to be basic. So we're going to use either a triethylamide, or we can use a pyrimidine. As our base. And so the base are net our net 3 or our pyrimidine. Either one of these two can be used. Like, it's not going to be both, just one of these two. They're going to take out the hydrogen from our OH, and the O is now going to become nucleophilic as it has a lone pair and negative charge once the hydrogen is removed. Right. So let's say the hydrogen is removed, for example, the oxygen being more electrophilic, electronegative than the hydrogen is going to take the lone pair and the negative charge, and then this oxygen becomes a good nucleophile and is going to attack our protecting group, removing the Cl in the process and binding to that group and then becoming protected, right? So this would be what our product would be at the end for this protection. Right, and so then we can have our Grignard reagent come in and react, do its thing, and then we just have to remove the protecting group with a reducing condition. So on top of what the net3 and the pyrimidine does, like they act as a base to remove the hydrogen, another thing that they do is that they prevent the hydrogen that was removed from the OH. So let's say this hydrogen here, and the Cl that was initially on the tosylate, sorry, on the mesylate, from combining, right? If they combine, it's going to make a strong acid. We don't want that. So the base helps us also make sure that that doesn't happen, right? The base makes sure that we take the hydrogen away from the Cl, right? So that would just be your ability to protect the groups. Tosylate and mesylate, particularly mesylate, is able to also protect amines if amines are close by, because amines can also have hydrogens that can be removed. Okay, the next thing we're going to be talking about is acetals, hematals, and cyanohydrins. So just to note what those groups look like. Whenever we talk about an acetal, we discussed this in our first lecture when we had functional groups. So an acetal is just two OR groups or two ethers attached to two other R groups, or a R group and a hydrogen, which means that you start off in this one, you start off with an aldehyde, and then you created your acetal. Or in this one, if you have two R groups initially, that means you start off with a ketone, and then you made your two R groups. So these are both collectively called acetals. So there is a way to, there is terminology used to differentiate between, if you start off with a ketone or an acetal. Like for example, a ketal would be the one if you start off with ketone. Acetal would be the one that if you start with a aldehyde. However, for terminology on the MCAT, you're not going to be seeing ketal. So just remember that acetal is when you have two OR groups as your substituents. When you have a hemiacetal, so as you can tell by the word by the prefix hemi, one of the groups, instead of it being another OR, another ether, it's just going to be a water molecule, right? These would be your hemiacetals. Okay, and then you're going to have your cyanohydrin. So whenever you're looking for acetals or hemiacetals, you're just looking for a carbon group that is bonded to two oxygens. For example, this carbon group bonded to two oxygens, these ones bonded to two oxygens. And it doesn't matter if like the R group on our ether right here is like a chain, like it doesn't matter if it comes like circles around, it goes over here, or this one circles around, goes over here. Just make sure that you have a carbon in which you have two, what's it called? Two oxygens, and then an R group for an acetal, and then then a carbon, two oxygens, one of them being a water molecule, the other one being, or an alcohol group, one of them being an ether, and then you have a hemiacetal. For the cyanohydrin, as the name suggests, you have a cyanide group and a hydrogen group. So a hydrogen can just be for example, a hydrogen just means water, like hydration, hydrogen, and then your cyanide group is just you're going to be your usual CN group. That's a cyanohydrin. Okay, so why are these relevant? Well, basically they're found a lot in like your biochemical molecules, like carbohydrates. And so how we can form these, right? So that's why they're important, like why we are studying them. But the formation of these groups. So I'm just going to erase this now. Actually, instead of erasing that, I actually have a slide in this presentation where we could do mechanisms and reactions. I just put mechanisms. So for the acetal and the hemiacetal formation, what we're going to have is the addition of a alcohol group with acid, and we're going to introduce those two to our ketone, for example. So remember that what we discussed today earlier on, that the carbonyl carbon of our ketone, or carbonyl carbon of our aldehyde, is electrophilic. And so for that reason, we're going to take advantage of that, and we're going to be attacking our electrophilic carbon with the alcohol group in order to make our either acetal or our hemiacetal. So first, let me just show you the reactions, and then we'll discuss the mechanism. So first we have, let's say, a ketone, and then to form the hemiacetal, so the hemiacetal is formed before the acetal. We have our acid, as we mentioned before, and then we have our alcohol group. And then from this, we're going to be forming the hemiacetal. Let's just say it's 1, 2, R1, R2, your OR group, and then your water molecule, your alcohol group. You have your ether here, your alcohol group. If you're to do this process again for a second time, let's say you introduce another alcohol molecule and you remove this group as a water molecule, so you subtract a water molecule, what you're going to have is the formation of your acetal from your hemiacetal as such. Okay, so how does this mechanism work, right? So basically what we did was if we introduce one alcohol group, then we're going to get the hemiacetal. If we introduce two alcohol groups, like if we continue this reaction, then we're going to receive eventually our acetal. And this can be, again, like the starting material we used here was a ketone. However, you can start all of this with like a aldehyde, right? You can just remove that R there, just introduce a hydrogen, and hydrogen, right? So the mechanism is the same for aldehydes and for the reaction is the same for aldehydes and ketones. So let's see the mechanism, see what happens here. So remember, as we discussed before, the OH group for the hemiacetal, for example, it's not a good leaving group. So in order to remove this OH group, we're going to have to protonate it first. But additionally, remember that the carbonyl carbon is electrophilic. And in order to make it more electrophilic, what we can do is move up this pi bond and move it up into the oxygen group so that we can remove the bond on that carbonyl carbon and make it more electrophilic. Okay, so what does that look like? Let's do the mechanism. Okay, so first, let's say we're dealing with this molecule here. In order to create a more electrophilic carbonyl carbon, what we're going to do is introduce the acid, right, from our reaction, acid, and we're going to introduce it, sorry, I drew that arrow in the wrong direction. The lone pair on the oxygen is going to grab that hydrogen. And if you think about it, like and then, we have this forming, right? If you think about it, if we were to do some resonance, what this does is it puts up the pi bond from the oxygen and it makes this carbon very positive, or AKA electrophilic, right? So that's the purpose of attaching the hydrogen group first to the oxygen. Okay, so once we protonate our oxygen group, what we're going to have is a very, very electrophilic carbonyl carbon, and thus our alcohol group is able to attack. And then the pi bond is going to go up like such. Okay, once we have this, we're going to have the formation of what seems like it's going to be a hemiacetal. The only thing that's missing is to remove the hydrogen off of the OR group. So once we do that, once we remove a hydrogen, we're going to effectively, let me just put a hydrogen here, let's keep this consistent. Hydrogen here, hydrogen here. And then once we remove that hydrogen from this OR group, like right here, we have a hydrogen on this oxygen that came initially from our alcohol. Once we remove this hydrogen, let's say a base picks it up. Base picks up this hydrogen. And then the bond from the hydrogen goes to the oxygen. What we're going to have is our hemiacetal. Right? If we were to continue this reaction, we would have our acetal. Right? So what does that look like? But what we're going to do is the same process in which we make our OH group a good leaving group. So the first thing we're going to do is we're going to protonate our OH. So we're going to have a proton here. The oxygen is going to pick it up. So let me keep this consistent. And then we have a H with 2 hydrogens on it, making it very positively charged. And then we have our alcohol group. This group right here is going to want to leave. Now that has become a good leaving group. Once this bond leaves and is taken by the oxygen, the lone pair on the the ether group is going to make a double bond with the carbon to prevent it from becoming a carbocation, right? Like such. This thing now has a positive charge as we have 3 bonds on the oxygen. The water molecule is going to drift off. After this, remember, if we were to move this here bond up there, we would make a carbocation over here, right? So we know that this thing has a electrophilic character on the carbonyl carbon. So what's going to happen is our other alcohol group is going to come in and tackle this electrophilic carbon. So what is that going to look like? Well, once we tackle this carbon here, this double bond is going to go back up. And what we're going to have is the same situation we had before, in which we have the positive charge on the oxygen. And then lastly, we just need to remove that last hydrogen from the HOR group minus the hydrogen. So we're going to be removing this hydrogen right here. And then we have our acetal. Okay, that is the reaction mechanisms for the hemiacetal and acetal. If you ever need to like stop and write down a mechanism, so you don't necessarily need to memorize these mechanisms. They're more useful just for learning the concepts. However, it wouldn't hurt to like know them. I've seen some passages on the full length actually have the mechanism of a certain reaction occur, so that understanding what the mechanism looks like beforehand, before you actually see in the passage, will give you a lot of time to become really efficient, right? Because if you already know what the mechanism looks like, you can work with what a reaction should be. Like they say, okay, like A plus B yields C, for example, and we're just talking about like a carbonyl, and we're talking about a acid and a alcohol group. And if you know what the mechanism looks like, and if for whatever random reason they introduce the mechanism to you, well, you're going to know what you're doing, right? And so the mechanism does help. If you're short on time and you're just trying to get through Orgo, like to know the basics, then recognizing or memorizing the mechanism maybe shouldn't be your first priority. Like the first priority should know the reactions. After that, maybe know the mechanisms. But again, these mechanisms are not too bad. It's really just the movement of hydrogens and making sure that everything that you do is the optimal step. So like first, we want to make sure our oxygen becomes a good, make sure that our carbonyl carbon becomes a good electrophile. How we do that? By protonating the oxygen. After that, we've made our carbonyl be a good carbon. Carbonyl become a good electrophile. Our alcohol is now able to attach. And then we're just going to remove the hydrogen, and then bam, we have our hemiacetal. So these mechanisms really aren't too bad. You really could just memorize them, lickety split. But again, like if you're tight on time, I would just really just know the chemical reaction first. Like this is the chemical reaction, and then if you have time, I would focus on the mechanisms. Okay, so now you can pause and copy this down. This is for hemiacetal and acetal. Now I'm going to show you guys what it is for what is the mechanism for the cyanohydrin formation. So it's really similar to that of the acetal, the hemiacetal. This thing can't erase fast enough. All right. That looks pretty good to me. Okay. All right. I just want to make sure that I'm recording, because if I'm not recording, I'm going to be tight. Ooh, okay, I'm recording that. All right. So let's do the mechanism for the cyanohydrin. And again, it's just the cyanohydrin being introduced to the carbonyl. Like we see it, we have a carbonyl here. Just want to introduce our cyanohydrin. Reaction occurs, and then we have, sorry, not our cyanohydrin, we're going to introduce our cyanide, and then we're going to have our cyanohydrin be the result. Okay, so what does this mechanism look like? Well, what we're going to have is this, let's say we're starting off with ketone. The cyanohydrin is in the very strong, what's it called? Nucleophile. For that reason, it has a counter ion. Right? The counter ion is the Na+. The Cn has initially on its own a negative charge. What we're going to do is we're going to bind onto this nitrogen with the carbonyl oxygen, making the carbonyl carbon very electrophilic, because remember, we can just throw up this double bond, and then we'll find that the positive charge will be lying down here. Okay, so we have the OH, sorry, we have the oxygen occupied with the Na+. And then we're going to have our Cn, being the good nucleophile that it is, come in and attack. And we have it here. After that, all we're going to need to do is to protonate our, sorry, I forgot that step, H+, or you could just put HCl or just acid. So acid. And after that, we're going to protonate our oxygen group with our acid. Let's just say it's H3O+, right? Well, this oxygen group is going to snatch one of these hydrogens. The bond that was found here, I just explained like this negative charge. If we had the nucleophile come in and attack, then it's going to bond here, right? Let's say nuke, like the CN was the nuke. And then this double bond is going to come in and flip up, and we're going to be giving an oxygen with X amount of electrons, making a negative charge. And that's why this negative charge here is able to interact not with a covalent bond, but with an ionic bond with this NaCl. That's just to explain what happened. Right? Okay, so we have the oxygen with a negative charge, ionically bonded with the Na plus. We have a acid group. We take one of the hydrogens from the acid group and we bind it to the oxygen. And at the end, we'll have our cyanohydrogen, like such. Right? This is the mechanism. Again, mechanism is really just to facilitate the understanding. If you have time, I would definitely memorize it, but only if you have time. Like, time is short. Okay. All right. Let me see if I could do something here. Let me see if I can highlight all. Oh, snap. Let's see if I can highlight all this and delete it. Oh, I think I can. Sweet. Sweet child of mine. All right. That was offered. Let's take these guys out. I don't remember what they're from. Did I even draw these? Yeah, sorry, there's probably going to be just minutes of me erasing the whiteboard, I guess. So next thing that I want to talk about to you guys is the amines, the imines, and the enamines. So if you recall, what the enamines are, is they are the nitrogen attached to an alcohol group. Sorry, not an alcohol group, sorry, a carbon group. An imine is when we have our nitrogen participating in a double bond, as such. And then our enamine is when we have, again, as the name implies, an ene, so En, means that we're having a double bond. And then an amine is our nitrogen is attached to a carbon group. So this is what an enamine looks like, right? So there's an amine, an imine, and then an enamine. Okay, so as we know, the nitrogen group prefers to have 3 bonds. And as it has 3 bonds, it prefers to, what's it called? It has a lone pair on itself, right? So let's say it's an R3 is going to have a lone pair on itself. And as it has a lone pair, that lone pair can bind a hydrogen, aka the nitrogen can be acting as a Bronsted-Lowry base. Remember, Bronsted-Lowry base can bind hydrogens, it takes up hydrogens. Or it can also act as a nucleophile, right? A nucleophile is something that can have lone pairs that can attack an electrophile. All right, so let's just go over the reactions that we have with amines, imines, and enamines. Well, we're not gonna really necessarily go into like the formation of an amine, like we just start with amines. Really, it's just about the imines and the enamines. Okay, so how can we create an imine, right? So for an imine, we're going to be using a primary amine, and we're going to combine it with a carbonyl group. It could be an aldehyde or a ketone. What we're going to need is a kind of a acidic solution, so it's called a buffer system. And it's going to be a low pH, so usually look around a pH of 4 through 5 that you have. And then you're going to be introducing your amine. Sorry, these lines are just horrendous. Like such. And then we're going to have our amine, say it's an R, and it's a primary amine, so just one R group that's attached to it. For amines, usually have a primary amine. And then what's going to result is just the replacement of the oxygen with our nitrogen. And the nitrogen has its R group, right? It's a primary amine. And then we have the removal of a H2O molecule. Okay, so that is the formation of an imine. So now the formation of an enamine is a bit different. What we have is going to be a ketone, and it's going to be reacting with a secondary carbon, right? So so pause if you need to write down this reaction. Okay, so what we're going to have for an enamine is our secondary carbon like such. And then we can have a secondary sorry, not our secondary carbon, but our ketone. And we're going to have our secondary nitrogen on our amine group. And with this, you still can use the same buffer system with a low pH. And with this, we're going to create our enamine. But let me draw. Let's give this something. Let's give this thing a structure. What we're going to have is nitrogen, the two R's on the nitrogen, right? It's a secondary nitrogen, it has two carbons on it. And then we have our double bond over here, right? And at the end, we have a H2O molecule. That is the reaction for the enamine. That's how we form an enamine, right? Okay. Let me show you the mechanisms before we continue on. So the mechanisms for the imine is we have remember, most of this stuff is just carbonyl mechanisms, right? So we just have to make sure the oxygen on the carbonyl becomes protonated, just to make sure that the carbonyl carbonate is a good electrophile and they're going to be attacking, blah, 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 right? So let me just show it to you rather than explain it, or show it to you and explain it. We're going to have our oxygen. Remember, we're in acidic solution for these reactions. Our hydrogen is going to come in, be bonded to our, let's say like this is our starting product, right? It's just a ketone. And then what we're going to have, right, so whenever you have the movement of a proton, it's a reversible step, right? That's what these two lines mean. They can go forward or backward. What we're going to have is the creation of this oxygen group. Now it has a positive charge. And now, with our carbon being more electrophilic than it was before, we're going to have our primary amine. Remember, this is for the imine mechanism. Amine mech. That doesn't look like mech. Mech, right? We're going to have our nitrogen. Say it has an R group. It has two H's, right? It has an H, has another H over here. The lone pair, remember, as we said before, it can act as a nucleophile. The lone pair on the nitrogens are going to come in and bind to our electrophilic carbon. And what we're going to have from here is, and then the double bond is going to raise up, because we can't have 5 bonds on a carbon. We're going to have the double bond raise up and go to the oxygen. As a result, the oxygen now is not going to have a positive charge, because now it has two groups. It has it's bonded to a carbon, it's bonded to a hydrogen, so it's not going to have that positive charge anymore. What we're going to have is our, start off with methyl, we start with the cyclopentane over here, and we're going to have our nitrogen group attached to it in R group, another hydrogen group, and another hydrogen group. There's there's 4 bonds to this nitrogen, but that's more bonds than nitrogen prefers, so it's going to have a positive charge, right? Next, what we're going to have is the removal of one of the hydrogens from the nitrogen, let's say from a base. The base is going to take one of those hydrogens. The bond from the hydrogen is going to go back to the nitrogen, right? And as a result, what we're going to have is, also, in addition, the oxygen group decides to take the hydrogen from a base. And yeah, that's the thing I forgot to mention. So actually, the protonation of this oxygen group first is important. As we have an HB, for example, and then this thing becomes a base because it had its hydrogen removed. This base is just going to come travel down here and then take one of the hydrogens from the nitrogen. So first we have the protonation of the oxygen, and then we're going to have our base or whatever that was holding on to that hydrogen come all the way down here, say, I kind of lost one, I want to take one back. So it's going to take it back from the nitrogen group. And as a result, what we're going to have is an OH2 here. So we have a positive charge on our oxygen. And we're going to have a nice and steady NRH group, right? A nitrogen that's bonded to a carbon group, and also that's bonded to a hydrogen. It's not going to have a positive charge anymore because it doesn't have 4 bonds. It just has 3 bonds. So now that we have this group, what we're going to have after this is the water molecule is going to come in and take, sorry, the water molecule is going to come in from this, like this water molecule right here, is going to come in and take those electrons from our group. And with that, what we're going to have is the nitrogen is going to prevent the carbocation forming from this carbon, because remember the oxygen, the water molecule is going to come in and take these electrons, right? These electrons are going to go over here, which means that the electrons are going to be gone from this carbon. So instead of making a carbocation, the nitrogen is going to take the lone pair that it has over here and it's going to double bond with the carbon. So what we have here is the removal of that water molecule. So this water molecule is now gone. It's over here. And we're also going to have the nitrogen double bonded to our carbon group. And it's still bonded to an R group and it's still bonded to a hydrogen group. So it does have that positive charge. Okay. After this, all we have to do is remove the hydrogen group from our compound, from our nitrogen. So you have an R here, hydrogen here has a positive charge. Well, the base is going to come through, snatch this hydrogen. Those electrons are going to go towards back to our nitrogen, and we're going to have our product, right? The imine. So that's how this mechanism works, right? We have the protonation of the oxygen over here to make this carbonyl carbon a good and electrophilic. Then our nitrogen with its lone pair that it has going to come in and bind as a nucleophile. It's going to attack as a nucleophile. The HB group, or whatever group that's present in your solution, is going to be snatched. Its hydrogen is going to be snatched away by our oxygen group here in order to make this group a good leaving group. Remember, the OH by itself is not a good leaving group. It has to turn into water first before it can become a good leaving group. And then the base is going to travel down here, take one of the hydrogens from the nitrogen. Now the nitrogen, now that the leaving group is taking the electrons away from the carbon and leaving on its own to become a water molecule, the nitrogen is going to form a double bond, creating this structure here, the species. And then the base is just going to come in and remove that hydrogen that's causing the positive charge, and then we have our imine. Okay, so you can pause this right here to write down the mechanism. And the only difference between the imine mechanism and the enamine mechanism is really the last step, right? This step right here. So like if we were to like just rearrange a couple things, what we would have is that rather than have a hydrogen here, remember our enamine, so let's just write that down over here. And mechanism. For our enamine, we're going to have a secondary nitrogen. So we have another R group here instead of a nitrogen. Over here, we have an R group instead of a hydrogen. Sorry, R group instead of a hydrogen. We're going to have a secondary R group right here rather than the hydrogen. Over here, we're going to have an R group. So the same mechanism, the only difference is just that that hydrogen that was tailing along with the nitrogen is going to be an R group. And what's going to happen is that rather than the R group be removed from the from this here nitrogen, what's going to happen is the base is going to take a, what's it called? I'm at a loss for words. It's going to take a hydrogen that is alpha to the double bond of the nitrogen. So remember we talked about for the carbonyl, how we had a alpha hydrogen that is likely going to be, has acidic tendencies due to the, like say we deprotonate it, we're going to have a negative charge here. And then you have resonance stabilization, right? The same thing occurs with the nitrogen. So now our base, instead of removing an R group, is going to remove a beta, sorry, it's going to remove an alpha hydrogen. It's going to remove most likely this alpha hydrogen. Actually, no, it wouldn't remove that alpha hydrogen. It would most likely remove this alpha hydrogen, which remember, for a carb anion, we prefer to have less substituents, right? Because we want less induction for a carb anion. So we're going to have the base here. We're going to snatch this hydrogen. These electrons go here. And what we're going to have is once we have those electrons there, is we're going to let's draw that out first. So R, this thing is still positive. Let's just show what that looks like. It's going to have a lone pair there, so it's going to have a negative group. What's going to happen, let's just remove this for now, just put it down here, right? This is the base I removed the alpha hydrogen. What's going to happen now is that this electron group is going to come in and make a double bond here, right, as resonance stabilization. So we're going to do some resonance structures and remove this lone pair to the nitrogen that was once a double bond. Sorry, not the lone pair, the double bond character. We're going to remove it from the double bond, and we're going to put those electrons towards the nitrogen. So that way nitrogen now has its lone pair back and only has 3 bonds to itself. And then we have our enamine as such, right? So let's run through this mechanism. So first we have our ketone. We're going to protonate it just to make sure, because, okay, I just want to make sure you guys see this again. So if we had a ketone like this, sure, I mean, as we mentioned before, due to this double bond moving up here, we can see that the carbonyl carbon is going to have a positive charge, right? Well, another way to facilitate this, to make sure that this is really, really present, what we can do is protonate the oxygen, giving this a positive charge. And since the oxygen really doesn't want to have a positive charge, it's going to move its double bond up, right? To make sure that it has just only 2 bonds. And that makes this electrophilic, sorry, that makes this this carbon way more electrophilic than it was before. So that's why we first protonate the oxygen on the carbonyl. So we protonate the oxygen on the carbonyl. Our a secondary amine is going to come in and bind, right? Because it has a lone pair of its own. It's going to bind on that electrophilic carbon, and then we're going to have our base. It's going to have one of its hydrogens removed by the oxygen. The base is going to travel down. It's going to remove the hydrogen off our secondary amine. After that, we're going to have the water molecule remove itself. We're going to have the amine double bond to our structure. We're going to have this group right here. So you really can't just, deep protonate a R group, right? The R group is not a proton. So our base is, rather than, before in the imine, we had just the final hydrogen removed, right? But in this case, the final hydrogen is going to be removed from an alpha hydrogen. It's going to be removed. And then we're just going to have some resonance to make sure we have no charges. And then we have our enamine formed. Okay, so that's the mechanism for enamine. I'm going to go ahead and erase it now. That's so convenient. Okay, perfect. All right, so that's enamine and amine, what's it called? Mechanisms and reactions. So now, as you can probably tell, kind of like with our keto and our enol, and enamines and imines happen to very look like tautomers, and they actually are. They're tautomers of each other, right? So a tautomer is just something that can interconvert between its constitution isomer. So let's draw the tautomer. So say we have an imine. Then if we have the enamine, all it is, say we have a negative here, right? Well, this is going to move down here. This is going to move up there. We have a negative rather on our nitrogen, and then we're going to have the enamine, right? So here we have the imine, here we have the enamine. They're tautomers. They can interconvert between one another, right? Well, what we can do with this is actually have a reaction in which what we do is add, as you can see right here, this here negative charge on this carbon makes this group right here very nucleophilic, right? This carb anion is very nucleophilic, and what we can do with that is that we can actually replace the leaving group of an alkyl group, and thus have the alkyl group come in and bind right here to this alpha site. Okay, so let's draw that mechanism, right? Or what that looks like, what that reaction looks like. So let's say we have this reactant right here. And we're starting off with our enamine. So we have an R group, another R group. Right, say we have this, and we're going to form our tautomer. By doing that, we take the lone pair of the nitrogen and we double bond it, and then we move this guy up here, right? Because we have too many bonds on a specific carbon, right? It only allows 4. So we have a positive charge on our nitrogen group because it has 4 bonds now. And then we have a negative group right here. This negative group can be a very good nucleophile. What we can do is, like, let's say we have a halogen on an alkane. What we can do is kind of like an SN1, is that we can have, or sorry, an SN2, which doesn't have that much hindrance. What we can do is have the nucleophile come in and attack. The X, or the halogen, leaves, and the result is going to be the formation like that, and then you have our group. Our group is the formation of a chain like such, right? We can remove the leaving group, and then we can have this form right here. For both the enamine and for the imine, if we were to have them in an acidic aqueous solution, what's going to happen is that they're going to reform back into that carbonyl that we had initially, right? So if we had our product, our amine or enamine, and then we reintroduce it into acidic water, what's going to happen is that our carbonyl is going to reform. So if we say that we have this product, and really what our intentions were, so like let's say we had this initially, and our objective was to make this group, then what we're going to do is we're going to take this ketone, we're going to put it through a enamine reaction. So we're going to take a secondary nitrogen, and I have some acid in there, H3O+. We're going to create our enamine, and then we're going to add our, let's say, halogen with the alkane, and then combine those two to form our arm on that end, like such. And then to reverse enamines or enamines, what we're going to do is just reintroduce it into acidic water. And that would flush out the nitrogen, and then we will have our ketone back. Okay. If anyone wants to see this again, you can just pause it. Jesus Christ. We'll just have it like this. Right, so it gets out of the way. All right. I think that's the last thing I want to talk about. Yeah, enamines are ketone. The negative charge on the alpha carbon, blah, 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 nucleophilic. After the substitution, the amine can be reverted back to carbonyl with aqueous acidic solution. Okay, cool. So that's enamines, amines, and amines, or amines, sorry. So next thing we're going to have is the aldo condensation. So in the aldo condensation, what we have is the formation, like the reaction of what an aldo condensation is. It's just the formation of a beta hydroxycarbonyl. So this is a beta. So remember, this would be the alpha, and then this would be the beta. This is a carbonyl group, so it would be the beta hydroxy, like the OH group. What we're going to form is a beta hydroxycarbonyl from 2 carbonyl compounds, right? We're going to start off with 2 carbonyl compounds. We have the aldo condensation, and then we're going to what's going to happen is we're going to create this here beta hydroxyl carbon, right? So what does this look like? Well, what we're going to do is first recognize the fact that alpha hydrogens are acidic, right? The alpha hydrogens here, like if we were to introduce this, like let's say we were to introduce this molecule right here to base, then the alpha hydrogens are going to be removed by the base, and we're going to have what's it called? Enolization, which is the movement of the let's say we remove a hydrogen from this here carbon, right? And we have a negative group now. We do some resonance around, and we can have something like this. And basically what the aldo condensation is this here double bond coming in and attacking, right, a carbonyl's electrophilic carbon. That's what aldo condensation is, right? We first have the removal of the alpha hydrogen. We're going to have the resonance form a double bond over here. And then we're going to use this double bond to come in and attack this carbonyl. Once that double bond is gone, the oxygen can remake its double bond, and then we're going to have a, a beta hydroxycarbonyl. Right, so that's just a kind of summary of the reaction. We're going to go into depth a little bit further, a little bit later on. So you just have to remember that the alpha hydrogens are acidic, and then we can have the enolate ion form, and the enolate ion is going to attack the carbonyl carbon as it is electrophilic. After that, we're going to be talking about the kinematic and the thermodynamic products. And then, yeah, okay, so let's go over it. Okay, so for the aldo condensation, what we're going to have is two carbonyl groups. Let's say in this case, we're going to have two aldehydes. So this CH3 here. We're going to use a strong base, like NaOH, and we have it in water. We're going to use a strong base to remove the alpha hydrogens away, or to deprotonate the alpha hydrogen from our molecule. And then we're going to have as a product, so let's take 2X, we're going to be using two of these carbonyls. And then what we're going to have is, as our product for this here reaction, is the beta hydroxycarbonyl form as such. Okay, so that's the reaction, right? What's the mechanism? Oh, and it also has to be said that we are also going to introduce a acid at the end in order to protonate our oxygen. Okay, so really quickly, what does this all look like as a mechanism? So remember, the mechanism is just used to facilitate understanding, and for the aldo condensation, the mechanism is really important. I would say if you were to like memorize any mechanism, I would say remember the aldose mechanism. So what we're going to have here for our mechanism is the carbonyl group is here doing its thing. One of the hydrogens is going to be snatched out by our NaOH. So this comes in and takes this hydrogen. The hydrogen sigma bond goes to the carbon. Now we're going to have a negative charge on this carbon. After that, we're going to do some resonance stabilization, as we mentioned before, to make our enolate ion. Remember, an enol is a double bond and an oxygen and a alcohol group. So an enolate ion is when our alcohol group just has been deprotonated, right? This is what, move that here, we move this up here. This is our enolate ion. Jesus Christ. And after this, we're going to have our second, because remember we have two of these carbonyls, of these aldehydes. And what we're going to do is introduce this double bond, right? This double bond can act as a nucleophile, come in and attack our let me just redraw that better. It's going to come in and attack the electrophilic carbon on our carbonyl carbon. It's going to attack there. You can't have 5 bonds on this carbon right here, so this moves up as such. Just continue forward, and what that looks like, this carbon right here is going to come in and tackle this. What's it called? It's going to tackle this carbon, destroying this double bond. And since that double bond is leaving, we're going to have the lone pairs on this oxygen group kind of come down sweep in and create another double bond. So we're going to have, like, let's say, let's start from here, right? Let's start with this molecule. What this molecule look like? This molecule is going to have our methyl group here, right? It's going to have the hydrogen group here. It's going to have the oxygen group that has just been created from the double bond, like such. And then it's going to have this covalent bond now to this here carbon, right? So that would be this carbon right here. What is this carbon attached to? It's attached to another carbon. Let's draw that carbon. And what is that carbon attached to? Well, this carbon is attached to a carbonyl, right? So attached to a oxygen as such. And it's also attached to a hydrogen, right? So this would be the formation of our aldo, right? And then at the end we introduce our acid, and we protonate our oxygen with the acid, and then we'll have our aldo condensation, right? A beta hydroxycarbonyl, right? So alpha right here, and then beta, this would be your second group. Alpha right here, beta would be right here, and then we have the OH right there, right? This is our beta hydroxy. Okay, so this is the mechanism for the aldo condensation. If you want, you can pause it and just copy it down. All right, so next, right, this is just the aldo condensation. It really just takes a lot of practice, like just find problems on, you can find some problems in the TPR book. Like the TPR book has a bunch of problems that you can practice for the aldo condensation. Or you just come to me definitely for office hours, you can talk about it. So let's say we have a ketone. Let's talk about now the thermodynamic product and the kinetic product of a aldo condensation. So let's say we have a ketone here, and the ketones and the alpha hydrogens on the ketones are not symmetrical, right? Like if we were to split this ketone in half like this, well, then we have these alpha hydrogens, which are on a secondary carbon, and then we have these alpha hydrogens, which are on a primary carbon. Well, if you were to do a product, if you were to do a reaction, well, then which kind of product would you get, right? Like, would you have the enolate occur over here? Or would you have the enolate occur in this direction with the double bond on this direction? Well, it depends, right? It depends on what kind of reaction is this happening in. So when you have the reaction happening well, before we get to that, before we get to like the different the conditions that you can have, what we're going to be looking at first is the stability of the double bond, right? If a double bond has a lot of substituents on it, then it's going to be really stable, right? So if our double bond was something like this, it's nice and cozy. It has a bunch of carbon groups surrounding it. It's nice and stable. And then after that, let's say we had removed one of those groups. So now it's less stable. Let's say remove two of those groups. Now it's less stable. It's kind of weird looking. Let me just redraw that. Let's say we had two of these groups removed. Now it's less stable. And then now it's less stable with this. And yeah, like this is like a primary end. This is a secondary one. This is kind of bad. Here we have two secondaries. Here we have a tertiary and a secondary. We have two tertiaries, right? So it prefers to have a bunch of substituents, right? If it's going to be stable, right? The more substituents it has, the more stable it is. And so for that reason, whenever we're doing our thermodynamic or a kinetic product, the thermo product is going to have the double bond on the more stable configuration. Like the double bond is going to be more substituted, more sub. In the kinetic, the double bond is going to be on the least sub group, right? Like in this case, in this scenario over here, we have a double bond on a primary and a secondary. Okay, it's not bad. And then here we have the double bond on a secondary and another secondary. So this one would be the thermal, right? Because it has more substitutes. So why thermal and kinetic? Well, thermal just means that you want to have like the lowest energy kind of reaction, like it's thermodynamically favorable. And kinetic just means that you want to have a fast reaction, right? Just it doesn't matter if it is what's it called? If it's on the more stable one or not, it just wants to be fast, right? Okay, so how can we make sure, how can we alter the environment of our reaction so that we can make sure that we get either the thermal product or the kinetic product? Okay, well, let's look at this reaction. Let's go back to our slides real quick. And we see that if a ketone is asymmetric to arms, then the alpha hydrogens are not equivalent. And you can have either a thermodynamic product or a kinetic product, right? So the reactions for a thermodynamic product is going to require a strong base that is small, right? And NaOH is a small kind of base, very strong, and it's going to have heat, right? A thermodynamic is going to require heat, so a small base with heat. However, if we want the kinetic product, what we're going to require is a bulky base, like an LDA is a bulky base, and we're going to require really, really cold conditions, right? Okay, so like, why would we, like, what would these conditions do, right? So for the thermal, the removing of the alpha hydrogen from the more sterically crowded alpha carbon is favored, right? So the more substituted double bond. And the kinetic, removing the less sterically hindered alpha hydrogen with the bulky base is faster than deep protonating the sterically hindered one. Thus, this is the one that's under the kinetic control. So what does that mean? Basically, if we have, for example, the cold condition, remember the cold condition is we have a bulky base and really cold degree, like -78 degrees Celsius, not even Fahrenheit, Celsius. Well, if we have a bulky base and we have like low, really cold conditions, well, then that bulky base is going to like snatch the alpha hydrogen that the fastest one that it can, right? Okay, which alpha hydrogen can I really just snatch away and like be happy, right? That's what this bulky base is asking itself. Well, if we look at this primary carbon, we have 3 hydrogens that I can take away from. There's nothing really sterically hindering this bulky base. However, if we looked at this secondary carbon group, what we're going to have is like a lot of steric hindrance involved. And so this bulky base is not going to be attacking these hydrogens. It's rather going to be attacking the hydrogens on the least substituted carbon. And that's why the chemists prefer to use an LDA or a bulky base for the kinetic reaction, because they know that the bulky base is not going to remove hydrogens from this more substituted carbon. Rather, it's going to take hydrogens from the least substituted, right? So we can make sure we confirm that we're going to have the double bond on the least substituted configuration, right? This one has more substituted, this one has least substituted. So, and then the condition for the fast, or the, sorry, not the fast, the thermodynamic product, we're going to have it in some heat, right? So that's the sign for heat. That's the triangle, or my attempt at a triangle, or you can have like 25 degrees Celsius, or you can just have this triangle, right? That signifies heat. If you have something like this, the small base is going to be easily able to, deprotonate either, but to make the more stable, we have heat, like we're going to look for the most stable, we're going to remove it from the more substituted carbon. So what would this reaction look like? Well, let's say we have 2 different settings for our reaction. Let's say we have this group here, right? We have an isoprop here. And then what we want to do is we want to sort of, and when I put pH, that means that we have a like benzene. And remember, for the alpha, like the removal of an alpha hydrogen, well, the alpha hydrogen must exist, right? So if we have like a benzene over here, benzene is like doing its thing. Let's just say like this. Let's just, I know that's a pentene, but like let's just say that's a benzene, right? There's not going to be any hydrogen groups here, right? There's not going to be any hydrogen groups present. So you can't have the, and let's say let's just draw another one. if we have something like this, right, this is going to be the, like if we were to not abbreviate this, we were to draw out the structure, well, there's not going to be any hydrogens removed from here, from the alpha carbon, because there's no hydrogens there, right? Because that carbon already has the max amount of bonds that it can have, right? It has 4 carbon, sorry, it has 4 bonds to it. And so this system right here is definitely going to be the one that's attacked at the carbonyl carbon, right? This is going to be the system that has alpha hydrogens, that has alpha hydrogens over here, has an alpha hydrogen over here. This is going to be the one that acts as the nucleophile, that's going to come in and attack this, this electrophilic carbon, right? So let's say we have these reactions. I'm not sure what that little squiggly is at there, the end. So you have a pH, so there's no alpha hydrogens on this carbonyl. So this one's going to be the one that's attacked, right? And we have in this one the LDA, then negative 78 degrees Celsius. And this one we have the NaOH, and we have the heat, right? So in this situation, the LDA is going to be forming the double bond on the least substituted, and in this case, in the NaOH, with the heat, we're going to have the double bond on the more substituted end, which means that this is going to be the nucleophile that comes in and attacks the carbonyl group, and then this one, on the other hand, would be the nucleophile that comes in and attacks the electrophilic carbon on the carbonyl group. And so the products for these reactions is going to be as follows. For the LDA, we're going to be having the carbon from the pH group, like from the nucleophilic group. Let's just draw the oxygen here, right? This oxygen corresponds to this oxygen. This pH and this pH correspond to these two pHs. So this carbon was the one that was attacked. So let's draw it from this direction, right? This carbon would be this carbon, right? Because this carbon attacked here. And then let's draw the rest of our product, right? So we have that carbon there. What is that carbon attached to? Well, that carbon is attached to a carbonyl group, right? So it's 1, 2. And this carbonyl group is then attached to everything else, right? Just the isopropyl group here, and then this here, methyl. And now let's look at our NaOH. The product is going to look like this, and all you really have to do is just remember where your attack was, and then just draw accordingly, right? So you have the pH here, the OH here, and we have the pH here, right? We have the pHs over here because this carbon right here, aka this carbon, attacked right over here, right? So we have the OH, and then we have the pHs over there surrounding. So this would be the aldo condensation, when we have a thermodynamic, or we have a kinetic product. Okay, so now could pause this. Next thing I want to talk to you about is if we have a strong base interact with our beta hydroxy group. If we have a strong base deprotonate the hydrogen from this oxygen group, from the alcohol group, what we're going to have is a retroaldol reaction, in which the kind of 2 carbonyls that this thing was made from are just going to come back and be formed. Okay, so what does that look like? Basically, let's draw it out. So let's say we had this as our reactant, right? We have our ketone right here. We have our beta down here, 1, 2, 3, 4 carbons. So let's just say that this initially came out from an aldo condensation from these two, right? A aldo condensation with these two forms this, right? Just upside down. So you can see the mechanism better. And then let's say we have a base here. If we introduce this, to, let's say that this has been, what's it called? We have our base, and then eventually we have our acid. -3 plus. Let me go to my notes real quick. So once we have that, we're going to form this group right here. And then the base is going to come in. Let's say we introduce, okay, so we have product. And this product is like this. And then we introduce the product to a strong base like NaOH, for example. What we're going to have is the base come in and take this hydrogen group. The sigma bond that's part of the hydrogen group is going to go back into the oxygen. Or rather than go straight back to the oxygen, because that's just a second step, it's going to go back into the oxygen. And once it goes back into the oxygen, it's going to go back into this carbonyl. Carbon is going to make a double bond, forming a carbonyl. And then this bond between this carbon here and this carbon here is just going to make a double bond. So it's going to just move. And this, if you have a sigma bond being removed, then what you're going to have is a cleavage, right? So this sigma bond no longer exists. So these two things are now untethered. And then we just have the double bond here move up to this oxygen, right? Because it kind of just looks like a cycle, right? Just boom, 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 boom. So the base is going to take the hydrogen gives its electrons back to the oxygen. Okay, now the oxygen creates a double bond, right? Because it doesn't want to have, it doesn't want to have a negative charge. So it makes a double bond. Okay, so now that this carbon now has like a double bond over here, and then a bond here, and then a hydrogen initially here. So just to make sure it doesn't have 5 bonds, just going to destroy the sigma bond and move it over here. So now this group has a double bond. Now that double bond is going to push this double bond from the carbonyl all the way up into the oxygen, right? And our product would be simply this. Have another hydrogen, and then we have our enolate like so. And if you just want to protonate this enolate, all you would have to do is just throw in a little acid, and then our oxygen group is going to be protonated. Okay. So now let's talk about next the last step for our aldol reaction. So I'm going to erase this now. So the final step for our aldol reactions is if we have an elimination, right? We have a what is called an elimination reaction or dehydration. Basically, what we're going to have is the OH group or the alcohol that was on the beta carbon of the carbonyl. Say we have an aldehyde. What we're going to do is, if we were to heat up this, this initial product from this reaction, right? Okay. These two had an aldol condensation. If we were to take the product of these two, like this product right here, and if we were to subject it to heat, what would occur is that if we were to add a little bit of acid, what would happen is that the oxygen here is going to be protonated by the acid. It's going to create a good leaving group, and then the and then with this, sorry, yeah, I didn't need to add this hydrogen here. Sorry. Just have it like this. Basically, what's going to happen is the removal of the H2O group, in which we can create a double bond. Right, so if we add heat to it, what's going to happen is this molecule. Okay, yeah, I'm sorry. This should have been there. So the mechanism is a bit tricky to follow. Basically, what we have here is the removal of this OH group and the creation of a double bond as such that is conjugated with the carbonyl that we have placed over here. So this is what we have a aldol elimination step. It occurs dehydration, and the alpha beta unsaturated carbonyl compound is formed. So what it means by dehydration is, oh, okay, I get the mechanism now. Yeah, I was kind of like really unsure for a hot second, but then I just figured it out. All right, so basically what we have here is this group here is going to be bouncing off, right? It's going to remove itself, it's going to go away, and what we're going to have as a result is a positive charge, and we're going to have a carbonyl like such. And what's going to happen is that in alpha hydrogen, one of these alpha hydrogens here is going to be removed, right? It's going to be removed, and once it's removed, what we're going to have is a negative charge on our carbon, right? Because the hydrogen is going to leave its electrons behind. And then it's going to form a double bond here, right, where you had your carbocation. So the mechanism isn't the most important thing. Just know that the OH becomes a good leaving group. It dips. A hydrogen, an alpha hydrogen, is removed. And it then has a carbon anion. The carbon anion then forms a double bond over here, creating a conjugated system, right? A double bond. Here over there, we have a carbonyl group. So that's the aldol elimination step, right? We add some heat, and then we get from this product into this product. Basically, the OH group just goes away, and we get a double bond here. Okay. So let's continue onward. Hopefully this hasn't been too long. I feel like it's been an hour already. We're pretty close to finishing. We just need like 3 more slides and we're done. Okay, so we're going to go over carboxylic acids. Again, our carboxylic acid looks like this, right? This is our carboxylic acid. As we can tell, we have, if we were to put 2 carboxylic acids next to each other, we have a hydrogen bond donating group, or we have a hydrogen covalently bonded to an oxygen, and we have a hydrogen bond acceptor group, right? Like this lone pair right here. So carboxylic acids have the ability to hydrogen bond, thus they have a really high molecular and high, sorry, not molecular, high melting point and high boiling point. A way to reduce carboxylic acids, remember carboxylic acid is just a primary alcohol that has been oxidized until it became a carboxylic acid. What we can do is we revert back this carboxylic acid back to its primary alcohol form. And the way that we do that is with a reaction as such. This would be the reaction that we get when we're trying to reduce a carboxylic acid back to its form. We're going to be using LiAlH4 with some acid. And we're going to get our primary alcohol back. Now, the reason we use specifically LiAlH4 is that it's a better, more stronger reducing agent than, let's say, NaBH4. So we're going to be using this specific reaction to convert this carboxylic acid into our alcohol group. Okay, next, what I want to discuss is that if we have a beta keto acid, so I'm just going to erase this. If we had a beta keto acid, remember what beta means? It means it's 2 carbons away from the carbonyl group, something as such. And if we have a beta keto acid, so this carbonyl is beta to this carboxylic acid group. If we have a beta keto acid and we introduce this beta keto acid to some heat, what's going to happen is we have a decarboxylation effect, basically what the decarboxylation effect is that as you can see in a carboxylic acid, there's an oxygen here, and this is an oxygen here. Remember, if you know what a CO2 molecule looks like, this is what a CO2 molecule looks like. So what's going to happen is this oxygen here and this oxygen here is just going to roll off and bounce, leaving this molecule plus your CO2. This is a decarboxylation of a beta keto acid. So I'm going to draw the mechanism for you down below. So it'd be like heat, right? And then a beta, what's it called? Keto acid turns into just a carbonyl with a CO2 group. So let me draw the mechanism for you. So what the mechanism looks like is as follows. We're going to have a ketone, and we're going to have a, sorry. We're going to have a ketone here. Just redraw that. We have a ketone here. Next, we're going to have our carboxylic acid. I'm going to be pointing in this direction just to make the mechanism easier. And what's going to happen is that the double bond from this here beta ketone is going to come in and steal this hydrogen from the oxygen over here. The covalent bond that's between the hydrogen and the oxygen is now going to be put back into the oxygen. And now that we don't want to have like a double bond necessarily on this here carbon group, this double bond now flips up, and in conjunction, this sigma bond between this carbon and this carbon, between these two carbons, is just going to go and rotate in this direction, right? So basically, we have the removal right here. So like this sigma bond came in and made a double bond over here, making effectively this group roll off. The resulting group that rolled off is going to form a double bond to a carbon, making a CO2 group, right? This is a CO2 group. So the hydrogen from this oxygen was removed by this oxygen, and then the double bond formed, and then just bounced off just to make sure there wasn't a lot of bonds here, and then the sigma bond just rolled off and went to this carbon over here. So this is our product. Next, just to finish everything off, we're going to have a nice little molecule holding a hydrogen for us, just kind of be attacked by this double bond. We're going to snatch that hydrogen, and as a result, what we're going to do is, in addition to the removal of this double bond right here to this hydrogen, what we're going to have to do is make sure that a carbocation doesn't form. Remember, because there's double bond, if it gets removed, the hydrogen is just going to go onto this carbon. Now this carbon is losing electrons. So what the oxygen does is that it moves the electrons down and forms a double bond with our carbonyl carbon. Now this thing is fully protonated, right? Because the double bond took the hydrogen from this base, and now this base, is kind of upset because his hydrogen was stolen. So the base is just going to remove that excess hydrogen from the oxygen species. And then this would be this is going to take it from here. This group is going to go back into the oxygen, and this would be our final result, right? This is the decarboxylation. This is the decarboxylation of the beta keto acid. Okay, so now that's the mechanism. You can pause and jot it down. All right. Next, what we're going to be going over is the carboxylic acid derivatives. Now, for the carboxylic acid derivatives, what you need to know is that we're going to be performing what is called a nucleophilic addition elimination reaction, right? So before we just had just the what's it called? The carbonyl group kind of just like dissipate out. You know, like we had this. Let's say we had this, and we had a nucleophilic attack. Well, basically, we just had like an addition, where like this OH went here, and then our nuke was here, and then our other group was here. When we're doing nucleophilic acid derivatives, when we're talking about carboxylic acid derivatives, what's going to happen is an addition and then an elimination reaction. So what does that look like, right? So all of our carboxylic acid derivatives have addition elimination reactions. So what that looks like, just the basic mechanism, is that we have this ketone here. Let's say we have the unspecified region. Why? Because we have like different kinds of carboxylic acid derivatives. We have like the carboxylic acid. We have the acyl halide. We have the ester. We have the anhydride. And then we also have the amide, right? So just say it's unspecified region. We have the nuke come in, attack the electrophilic carbon here. That's the addition. This double bond is going to go up to the oxygen, as it usually does. As oxygen has a negative charge, like the electron going back up into it. We have our nuke here. So we have the unspecified region over here. And now, as we said, it's going to be an addition. So the addition happened, but now we're going to have the elimination, or the elimination of two sigma bonds to form a double bond. And so the group from the lone pair that's excess on this oxygen is going to come back down. And what it's going to do is that it's going to pop off the unspecific region. And so we can have our carbonyl back with our new nuke. And then we have over here the unspecific region. So that's the addition elimination reaction that we're going to have with acid derivatives. Okay, so if you need to copy that down, I'm just going to erase it now. Just pause the video. Okay. So next, we're going to talk about specific reactions that you can have with your carboxylic acid and its derivatives. For example, you can have an esterification reaction. So as it implies in the name, an ester is going to be formed from a carboxylic acid, right? Esterification. With hydrolysis of esters, what we're going to have is the removal of the ester group from the carbonyl, and we're just going to have our carboxylic acid reform. Right? It's just going to come back. In trans-esterification, what we're going to have is the removal of one ester with the conversion of that ester to a different ester. So basically, an ester is exchanged for a different ester, right? Like we'll explain what that looks like. But basically, the OR group for the ester is going to be replaced with a different OR group, right? It's just a trans-esterification, just the removal of one ester to make another one. And for these first three reactions, the esterification, the hydrolysis of esters, the trans-esterification, they all, like all the reactants and the products and the intermediates, they all exist in equilibrium with each other, right? Like for the esterification reaction, we have the carboxylic acid, and then we have the ester as the product, and the carboxylic acid is introduced to an alcohol. What we find is that the reactants and the products are in equilibrium for each other with esterification, with hydrolysis of esters. And for the hydrolysis of esters, what we have is an ester form a carboxylic acid and a alcohol group. Again, these are in equilibrium. And then trans-esterification is just an ester 1 going to, sorry, I'm just drawing the arrow over here, going to ester two, right? There's just the difference between two esters, and they're in equilibrium with each other. The sponification reaction, however, it is not a reaction that is reversible. And what it is, it's base-mediated ester hydrolysis, right? So for the hydrolysis of esters, you usually have a acid catalysis. The acid catalysis would be the one that is in equilibrium. The base-mediated reaction, aka the sponification, this reaction is not going to, saponification. This reaction is the base-mediated ester hydrolysis is not going to be in equilibrium. So you're only going to have a product form for sponification. And what sponification is, it's just the ester being formed back into its carboxylic acid plus alcohol group using base. That's what sponification is. Okay, so now let us get into the reactions for all those. All right, so let's start off with the mechanism for the ester formation, so esterification. So let's say we start off with our carbonyl group. As always, we're going to be protonating our oxygen just to make sure that it becomes a strong electrophile, the carbonyl carbon. So we have well, before I actually start the mechanism, let me show you the reactions, like the reactions of these esterification, for example. Esterification, what we have is carboxylic acid. We have a alcohol group, which is going to be forming the ester. We have both of those in acid, and then we have the ester form, right? The OR rather than the OH, and we just have water, right? This is the esterification reaction. If we had the hydrolysis, however, what we would see, we have acid here, is just the reformation of our carboxylic acid. And then we have the reformation of our initial alcohol as well. Yeah, we have those two there. And then I'm just trying to figure out if we, yeah, oh, right. So, and then we have our trans esterification. So we have a carbonyl and an ester like such. We introduce it to a new alcohol, right? This is an ester plus the alcohol. We introduce an acid, right? It's in equilibrium with each other. That's what those double arrows mean. Those are actually arrows. Let's say 1 and 2. And then you're just going to form the other ester, R2 plus HOR1. And then sponification, what it is just like your, again, it's just your ester. It's not going to be in equilibrium, so just you're going to be in NaOH. And then you're going to form your carboxylic acid. This is NaOH and water, H2O. You're going to have your carboxylic acid, and you're going to have your alcohol reform. So these are the four, right? You have the esterification, you have the hydrolysis, you have the trans-esterification, and then here you have saponification. Okay, you can pause the video. And now we're going to go through all of the mechanisms. Oh my God, this is going to take such a long time. I am dying. And dude, it's like 11 o'clock and I still have to make the PowerPoints for the biochemistry pathways. Like I'm probably gonna go sleep at like 4 a.m. I'm gonna say, which sucks, but you just gotta do what you gotta do. All right, so let's talk about the mechanisms now. So for the what's it called? For the esterification, so the formation of our ester group, we're going to have our carbon. We have the acid, the oxygen binds to the acid. We have our R group. Now we have this positively charged. because it has a hydrogen on it. We still have our OH group here. And now this thing is a good ester. Like, sorry, this is a good electrophilic carbon. So we're going to have our alcohol group be able to attack our our very electrophilic carbon. Now this bond is going to go up here. After that, we're going to have, let's say this is the alcohol that just attacked. Let's say this is the resulting situation. Well, after that, what we're going to have is the removal of one of those OHs, right? Because one of those OHs is just going to have to be removed in order to create our elimination reaction. So another acid is going to come through, another proton. It's going to be absorbed by, it's going to be taken in by one of those OH groups. Consequently, upon the formation of a good leaving group, remember, an OH is not a good leaving group. However, when you have an H2O, you do have a good leaving group. Let's say we have the H and the R still positive. With this, you know, actually, I'm sorry, we should have removed the this hydrogen on the alcohol before we did anything else. So let's just start from here. What we're going to have is the base coming in and taking this hydrogen, and then that sigma bond is going to go back to the oxygen, and at the same time, we're going to have this oxygen pick up the hydrogen from that base, right? Like this base here just picked up this hydrogen, and then this HB is going to be donating its hydrogen to this oxygen group, right? So it's a concerted situation. And then we're going to have the R like such. We have the OH, we have the OR, no longer positively charged because the hydrogen was taken by this base. Now this group is an OH2 because that base that just picked up a hydrogen is now going to donate its hydrogen to this OH. Now this is a good leaving group, so we're going to have this thing be removed. Consequently, this here oxygen is going to create a double bond. What we're going to form here is then the bond to the oxygen. That's positively charged because it's still bonded to the hydrogen from before. The H2O molecule from that H2O that was there, and then we have our alcohol, right? Sorry, the OR group, the ether group. And then we're going to have that base again, that homing base, come in and snatch that hydrogen. The sigma bond is going to donate the electrons to the oxygen. Excuse me. And then we have what we want to have is the formation of our ester. That's the mechanism for ester formation. Now, let's talk about the acid catalysis of hydrolysis. Remember, hydrolysis is the removal of the ester and then to make the carboxylic acid. All right, so let's draw that out. Let's see. So we're going to have our ester over here. And with this, we're going to protonate our, so we have an H3O plus, we're going to protonate our oxygen to make it a good electrophile, a carbonyl carbon. An OR, we have a double bond here, and that has a hydrogen group, so that's positively charged. And now our water molecule is going to come in. Our water molecule is going to attack the carbonyl carbon, right? Because now it's a good electrophile, it's going to come in and attack, right? Resulting in the double bond over here to come jump up. We have an R, we have an OH here that was just recently formed. We have an OR here, and then we have an OH2 plus here, right? Well, after this, what's going to happen is a water molecule is going to just take one of those hydrogens from that other water molecule. So it's going to take one of those hydrogens, and that pair is going to go to the oxygen, resulting in a R group, a OR group here, an OH group here, and then another OH group here. Right? This is the resulting step. After this, what we're going to do is have the acid protonate our OR group in order to make it a good leaving group, right? So we have an OH here. Let's just say we just throw up the OH here, and then we have the OR group here. Our acid H3O plus is going to protonate our OR, resulting in the formation of a good leaving group. And H, now that's positive. Now this is a good leaving group. What we're going to have is the removal of this bond. It's going to go here, and then one of these bonds is just going to go down there, right, to make the double bond now that this other sigma bond is leaving. Remember, it's an addition elimination, right? We added the OH group and removing the OR group. So now we have a double bond over here. We have that other OH group can just come down, and then we have an HOR right here that just plopped off, right? Well, after this, all we have to do that's left is just to make sure that the water, let's just say an H2O, just comes in and takes this remaining hydrogen, and then we're done. We have our carboxylic acid back from our what's it called? From our ester, and this whole thing again is in equilibrium, right? Because all those arrows were reversible. Okay, now we're going to be talking about the base mediated reaction. Remember, we had an acid catalysis, and then we had a base mediated reaction for hydrolysis of the ester. So let's just say we have an R group here, a oxygen group there, an OR here, and let's say we had our base, right? Well, the base is decently nucleophilic. It doesn't really need to prepare, we don't really need to prepare this carbonyl carbon to make it super electrophilic, because it's a really strong nucleophile. So they just have those electrons pop up on the oxygen. We have a negatively charged oxygen here, we have an OR group here, and we have an OH group here. Next, what we're going to have is this group just really want to go and make another double bond, and this double bond shoots off this here OR group. This is actually a forward-facing reaction. It's not an equilibrium. That's why the sponification or the base-mediated hydrolysis of the ester is a non-equilibrium reaction. So we're going to result in double bond here, the OH here, the OR that just popped off is here. Now, which one is more acidic? Or sorry, which one is more basic? So basically what I'm trying to say is the carboxylic acid is a acidic group, and so it's going to be removing its hydrogen. And for that reason, the oxygen in sponification in the carboxylate ion is going to be there, and the OR group is going to take the hydrogen from your carboxylic acid and protonate itself, making an HOR, making a proper alcohol. Okay, so that last step is decently important. Definitely memorize that at the end, the hydrogen is going to be attached to the alcohol rather than the carboxylic acid, because the carboxylic acid is more acidic. So it's going to be popping it off, and the OR is going to be picking it up. All right, next, let's talk about your carboxylic acid derivative synthesis. So we have different carboxylic acids. Of course, we have your acid halides, acid anhydrides, esters, and amides. So you can make all of these from your carboxylic acid, right? Except for amides, but we'll talk about that. So for your acid halides, the reactions that you're going to have is, for example, an R to make it from the carboxylic acid. So you have an OH group here. Then we have an R and an H group here. Let's just say we have an SOCl2. For this reaction, we're going to be forming a RCl, which is a acid halide, or specifically an acid chloride. And in this reaction, we can have a sorry, that's not a P, a PX3, where the X can equal either a Br or a chlorine. So it can be PCl3 or PBr3, whichever one. And then this combines with our carboxylic acid, and we form our nice little product. Okay, so it says here, acid halides can be formed from carboxylic acids, right? We've just seen this. Now let's look at acid anhydride. So pause the video, write down these reactions. Okay, so and now let's see the formation of an acid anhydride. So acid anhydride can occur when you just have two carboxylic acids facing each other, and they just stare at each other, and then they combine. It's basically just what happens, right? You have the removal of a water molecule. Water molecule bounces H2O, HO2. No, sir. It's H2O. Okay. The removal of a water molecule, and the result, this hydrogen and oxygen, just those three atoms removed, making a water molecule, and resulting in your anhydride. Now it says here that an anhydride can be formed from a carboxylic acid, as we've just seen, or an acid halide, which means that if we're going to put an acid halide like such, and then we had a carboxylic acid, then what can happen is that your what's it called? Oh, sorry, I forgot this important step. Heat is required for the anhydride formation. So removal of water, and you're going to be introducing heat in order to form your anhydride from your two carboxylic acids. However, for the for this here group, let's see, we have an acid chloride, and then we have your carboxylic acid. We're just going to have those two combine, remove your Cl, and typically, this carboxylic acid is going to be deprotonated. It's going to be in this form. The Na plus is the Na is the counter ion. So you just have a removal of NaCl from here, and you're going to create your anhydride as such. Okay. Next, we have your esters. We already talked about the formation of esters. It can be formed from carboxylic acid, from the acid halide, and from the acid anhydride, and in general, remember other esters, right, with trans-esterification. So why does it kind of look like a ladder, right? This one can be formed from carboxylic acid. This one can be from carboxylic acids and acid anhydrides. This esters can be formed from all of these that are above it, plus carboxylic acids and other esters. Well, the reason being is that we are increasing. Sorry, we are okay. We'll get to that. Let me not jump the boat just yet. Okay, that was anhydride formation, esters we talked about. Let me just finish talking about amides, and then this concept right here before we get into the reactivities. So amides, the amides are like amides are formed with amines, right? You have an amine, for example. If we take a look at this carboxylic acid, the acid and this amine, rather than create an amide, which is this, what we're going to have is just a classic acid-base reaction, right? Because the nitrogen on the amine is really basic. This group right here is really acidic. This carboxylic acid is acidic. So what we have to do if we want to make an amide is we're first going to have to convert our carboxylic acid into an acid halide or an acid anhydride or an ester, and then we can form the amide from those other carboxylic acid derivatives, right? So let's say you just have your acid chloride as such, and then we can add it with an amine, and then we can have our amide form, right? So what's with this? Like, why is this? Like, what's with the ladder right here, right? What's going on? So what we need to know is just that these carboxylic acid derivatives have different reactivities, and what we find is that the Cl is the most reactive, and that's why the acid anhydrides can do it. The esters can start off from an acid halide. The amides can interact with an acid halide. Next in the reactivity is the acid anhydride. So we'll find the same pattern, right? The acid halides can't be formed from a acid anhydride because the acid halide is more reactive than the acid anhydride. So it wouldn't be forming the acid halide. It'd rather be, remember, if something's reactive, it means that it's going to be making something else, right? If you have a really reactive acid, if you have a really reactive acid chloride, for example, then you're not going to have your acid chloride by the end of your reaction, right? It's really reactive. It's going to turn into something else, right? Okay. And then next in reactivity is your R double bond carbonyl group ester. And then lastly, the least reactive or the most stable would be your R N, right? Your amide. So how do we determine if something is reactive or not? Well, basically, we just have to look at the removal of your group and what it would look like in terms of stability, right? So if we remove the group from the acid halide, remember, it's like this is an acid halide. If we were to remove the group from the acid halide, and what we would have is just this, sorry, this would be a positive, and the group would be a halogen. Well, let's look at a halogen, right? A halogen is what? A halogen is a pretty good leaving group, and it's also a weak base, so it's going to be pretty stable in the solution. That's what makes it really reactive, right? It can just easily pop off and allow all of these other reactions, like the anhydride formation. It can allow the ester formation, can allow the amide formation to occur, right? Because it's easily just popped off. Let's look at the other acid, carboxylic acid derivative, right? Let's look at anhydride. Let's see what it looks like when that group pops off. So when this group pops off, what we're going to have is it's this system right here, right? Like whenever this thing pops off, let's just say we convert it back to a carboxylic acid. This is the group that we're analyzing. Let's look at the stability of this group. Well, if we look at the stability of this group, what we're looking at, what we're trying to see is that the less basic you are, the more stable you are, right? Because the halogen is very stable. It's a weak base, right? We're just looking at to see if this thing is a weak base. If it's a weak base, then it's reactive. If it's a strong base, well, then it's not going to be popping off in the first place, right? Like if this was a strong base, the anhydride wouldn't be splitting off really easily, right? Like as it would if it was a chlorine. Because a chlorine, when it pops off, you can make a weak base. Okay, so let's analyze this here structure. Like, what is this? Well, it's just the conjugate base of a carboxylic acid, right? Like if we were to draw a hydrogen here, you just have a carboxylic acid. And remember, carboxylic acid is a decently strong acid, which means that its conjugate base is decently stable. So this group, and that's why the anhydride is the next group in terms of reactivity, because although it's kind of it's kind of a base, like this carboxylate ion is sort of like a base, kind of. It is still decently stable, right? But not as stable as the Cl or the halogen. Okay, next let's look at the ester. And what we'll see with the ester is when we pop it off, it's just going to be the conjugate base. If we pop this thing off, it's just the conjugate base of a alcohol, right? Like this is the conjugate base of an alcohol. This is what an alcohol would be like. And remember, an alcohol is really not that acidic. And if it's not that acidic, that means that its conjugate base, aka this OR group, is not going to be a weak base. It's actually going to be a relatively strong base, right? Because the more acidic something is, the more stable its conjugate base is. So if it's not acidic, that means that its conjugate base is actually not going to be that stable, making it a strong base. And that's why this ester is kind of down here in terms of reactivity, because this OR group isn't that stable. So it'd probably go back and try to bind rather than really be popped off, right? The Cl is really, this halogen is really just ready to pop off, right? Because it's a good leaving group, it's stable. Now let's look at the amide, right? Now the amide, on the other hand, when you pop it off, what you're going to see, let's just say that there's an R here and then an H. What you see is this group right here, and this group is just a completely super duper strong base, right? It's a really strong base. Remember, nitrogens are just strong bases in general. And for that reason, it's the least reactive, right? Because when it pops off, it's going to go back straight back to that carbonyl group and form that amide again, right? It's not stable in a solution. That's why it's the least reactive. So that's the end of it. Just so you guys know, in case you want to revert any of these derivatives, the halides, the anhydrides, the esters, or amides back into the carboxylic acid, all you would need to do is to heat your solution in some acid, right? Specifically, acid halides and acid anhydrides. You can even like put them back into carboxylic acid with just straight up water, right? Because they're really reactive. But the esters and amides, you want to make sure that you have a high temperature for your reaction, because those are relatively less reactive. Okay, guys, that's the end of the lecture. I hope I didn't take too long. I'll see how long it actually is. For me, it's going to be like 2 hours, but all right, guys, I'll see you tomorrow.